Okay, this question talks about a block being pulled up an incline. And so you'll see me change the direction of positive for this problem. So we're going up an incline. It doesn't matter how you draw it, but I tend to have my objects going slightly to the right. So I'm going to draw my incline like this. And then here's my block. It's being pulled up an incline by a force that's directed parallel to the incline. So there's an applied force pointed like this. Again, this is our theta that we know. So let's label our forces. Again, we have gravity, mg. Again, I may want to just put those components in with dotted lines right away, so I remember that that's how I deal with gravity on incline questions. If there's a surface, there's always going to be normal force, which is perpendicular to the surface. And then because the problem mentions friction, then I should put a frictional force in here as well. Again, the object I'm picturing, it's moving up and to the right, so my direction of motion is like this, and I will call that my positive direction. So my frictional force is going to point down the incline. So there are two forces working against the object's motion. The gravitational force, at least the component of it that points that way, and also the frictional force. The problem does not specifically ask me to look at both directions, but I will have to in order to answer the question. So let's go ahead and set things up. Again, I'm going to just use a line to organize my work. I'm going to begin with forces that are perpendicular to the incline and say that they must equal 0 because the object isn't actually moving that way. And then forces that are parallel to the incline are going to equal m times a. So perpendicular to the incline, again, we have the normal force, and we have the component of weight, mg cosine of theta. Those are going to have to equal 0 when I subtract them. So my normal force will be 1.2 times 9.8 times the cosine of 25. This comes out to be 10.66 newtons. All right, so I'll underline that. That's a number I'll need to use in a few minutes. In the other direction, we have quite a few forces to deal with. There's the pulling force, the applied force, the frictional force, and a component of the weight. So make sure I put all of those in. I have decided to call up the incline positive, and that means that I'll begin with the applied force as I list things. So that'll be a positive force. It's helping the motion. The frictional force, mu times F sub n, works against the motion. And then I also have this part of weight that's working against the motion this time. Oops, sorry, that should be the sign. mg times the sine of theta. So mg sine theta points down the incline, but it's moving up the incline, so it's going to be put in there as negative. All right, now in this case we don't know what mu is. That's our question mark, so let's put everything else in. Applied force is 15. Mu is my unknown. My normal force is 10.66. We'll subtract also that component of weight, so 1.2 times 9.8 times the sine of 25. Okay, that's everything from the picture, so that's on the left side of my setup. And on the right side of my setup, I know the mass, and this time I do know the acceleration is 3. And so I would work through some algebra. In most cases, mu is going to end up being a value that is between 0 and 1, positive decimal value. And in this case, mu ends up being 0.60. One more time, just to see some connections here. The left side of my setup comes from the picture, the good free body diagram. The right side of the setup are going to be values either that you know or that you're being asked to find. Notice too that since I'm working with friction, I have cosine in one part of my problem, I have sine in the other part. If there is no friction, you might not actually see that cosine portion in your setup at all.